everyone. Today we are learning a method for achieving high-quality speech coding at lower rates, adaptive differential pulse code modulation, also known as ADPCM technology. This lesson will be elaborated from the following 6 aspects. In 1972, the ITU established the G.71164 kilobits per second PCM speech coding standard. However, in practical applications, especially in scenarios with extremely precious bandwidth resources, like mobile communications, its high bit rate becomes a roadblock. Just as carrying too much luggage makes travel inconvenient, transmitting 64 kilobits per second PCM within a limited bandwidth is also challenging, whereas one analog voice channel occupies only 4 kHz. What is the reason? In PCM encoding, each sample value fights alone, being encoded independently, which requires many encoding bits, thus occupying a large bandwidth. So, how do we solve this problem? In 1984, the ITU introduced the ADPCM encoding standard G.72632. ADPCM is particularly impressive. It fully utilizes the correlation between speech signal samples and employs adaptive prediction and quantization techniques, perfectly addressing the non-stationary nature of speech signals. It can achieve high-quality voice transmission meeting public network requirements at a rate of 32 kilobits per second. Isn't that amazing? Next, we will delve into its principles. Before exploring the principles of ADPCM, we must first understand predictive coding. In predictive coding, we act like little fortune tellers, first calculating a predicted value based on the previous few sample values using a specific calculation method. Then, subtract the current sample value from the predicted value to obtain a difference known as the prediction error. Since the possible range of the prediction error is much smaller than that of the sample values, we can encode it with fewer bits, thus reducing the bit rate. If we use a linear combination of previous sample values to predict the current sample value, this is linear prediction. If we use only the immediate previous sample value to predict the current one, this is what we will discuss next. Differential pulse code modulation, DPCM. The principal block diagram of differential pulse code modulation, DPCM, is shown in the figure. The encoded signal is the quantized encoding of the difference EK between the current sample value MK and the predicted value MK. Although DPCM is already excellent, speech signals are highly variable and change over a large dynamic range. Achieving optimal prediction and quantization is not simple. Therefore, scientists added adaptive processing to the DPCM system, and ADPCM was born. Look at this simplified block diagram of the ADPCM encoder. The encoder input is nonlinear PCM code, such as A-law or mu-law PCM code. To facilitate digital signal processing, the 8-bit nonlinear code is first converted into a 12-bit linear code. Next, the linear PCM signal is subtracted from the prediction signal to obtain the prediction error signal. Then, an adaptive quantizer quantizes this difference signal and encodes it into a 4-bit ADPCM code for output, thus reducing the ADPCM speech signal rate to 32 kilobits per second. Compared to the PCM system, ADPCM's advantages are particularly evident. It can significantly compress the data rate and transmission bandwidth, like compressing a large file into a smaller one, not only saving space but also improving transmission efficiency. ADPCM has found wide application in satellite communication, microwave communication, and mobile communication, and has become an internationally common speech coding method in long-distance telephone communication. Generally, coding methods with a channel rate lower than 64 kilobits per second are called speech compression coding techniques. In addition to the DPCM and ADPCM introduced earlier, there is also delta modulation. Delta M can be considered the simplest form of DPCM. Delta modulation was born in 1946. Its core idea is instead of directly recording the absolute magnitude of the signal, it records the direction of change at each step, e.g., increasing or decreasing. It's like climbing stairs. Others don't ask which step you are on, only whether you are going up or down with this step. Next, let's talk about the encoding principle of delta. Assume this pink continuous waveform MT is the sound collected by the microphone, and the green line represents the predicted value. At time t1, the current value is greater than the predicted value, output 1 indicating increases. At time t2, the current value is less than the predicted value, output 0 indicating decrease, and so on. The most significant feature of delta modulation is that each sample point is represented by only one bit 0 or 1. That is, delta M has two quantization levels and a coding bit number of 1. However, delta M samples the signal tens of thousands of times per second, much higher than PCM. This table provides a performance comparison of 3 coding methods in speech signal digitization, each with its advantages and limitations. These 3 methods all belong to waveform coding. Furthermore, speech coding also includes parametric coding and hybrid coding. Parametric coding encodes by extracting characteristic parameters of the speech signal. Its goal is to maintain speech intelligibility at very low bit rates, rather than waveform fidelity. Hybrid coding combines the low bit rate advantage of parametric coding with the high-quality characteristics of waveform coding, employing an analysis by synthesis framework. Through algorithm optimization, hybrid coding continuously reduces the bit rate and improves sound quality, making it the preferred solution for bandwidth limited scenarios, especially in mobile communications. In 4G and 5G networks, adopted technologies like AMR, adaptive multi-rate, and EV's enhanced voice services belong to hybrid coding technology. Hybrid coding balances efficiency and quality. In your future engineering decisions, students should learn the doctrine of the mean from hybrid coding, seeking optimal solutions under multiple constraints and avoiding extreme thinking. That concludes today's lesson. Thank you.